In the last exercise, we drew the mechanism for imine formation of those nitrogen versions of ketones, by adding a primary amine. You add a primary amine to a ketone and it turns into that Schiff base, that imine. And we were thinking about the reasons why it happens step by step, opposite charges attracting to make that transformation. In this exercise, though, we want to do that, think about that same reaction, but in the context of synthesis. In synthesis, you're zooming out. You're not thinking in detail about every single thing that happens to make a reaction happen. You're thinking about what recipes can you use to transform one molecule into another. So we're going to think about that same reaction, but just in a different context here. Now, in these exercises, you don't need to draw out the mechanism. You just need to draw the product. So in these products, in these reactions, remember, all you do to form the imine, you take the same carbon chain, that all stays the same. Oops. But where you had the double bond to the oxygen, you now have a double bond to a nitrogen. Now the nitrogen forms 3 bonds. The 2 of the hydrogens that it was bonded to get replaced. Usually it's another carbon chain that's left, but if you start with ammonia, then the 3rd thing is just a hydrogen. And that's your product. Truly that simple. Notice that another product is water. That's what they're trying to get at here, that water is subtracted or removed in the process, because you take the oxygen from the ketone and you take 2 of the hydrogens off of the nitrogen. Well, that oxygen plus 2 hydrogens is water. And this is always an equilibrium reaction, so you can control this equilibrium in the same way that we controlled the equilibrium of acetals and ketones, using Le Chatelier's principle. So if you want the ketone, just add water, and if you want the imine, just remove water. And that's how living things control which of these products they want in their vesicles. They'll have the reaction happen inside of a membrane, semi-permeable membrane. They'll squeeze water out of it, and that'll make you form the ketone. Or they'll let more water in, and that'll make them form the imine. Okay. Or actually, I'm sorry, it's the other way around. If they remove water, then you end up forming the ketone. And if you let water in, you form the other way around. If you let water in, then you form the ketone. If you remove water from the vesicle, you don't form the amine. Anyway, with this next one, you're again just replacing the double bond to the oxygen with a double bond to the nitrogen. The 2 bonds on the nitrogen that get replaced are to the hydrogen. The R group is left there. So on the other side, we end up having that other cyclopentane ring. So this ring right here is this one. Just so happens it's the same type of ring that was on the original molecule. So when you're trying to draw the imines, the Schiff bases, just erase the oxygen, put the nitrogen in there, and draw in on the other side of the nitrogen whatever R group was there to begin with. So that's 2016. 2017 is the same idea, but this time it's happening inside of one molecule. And this is something we've seen before. In the case of acetal formation, we saw how sugars are aldehydes with lots of alcohols on them, or ketones with lots of alcohols on them. That's what a sugar is. That's what a monosaccharide is. And the alcohols on one part of the molecule can come around and act as a nucleophile and attack the aldehyde or the ketone to form a hemiacetal. It's an intramolecular reaction. Well, similarly, biomolecules will have these functional groups on them in different places, and they can react with themselves. Now, if that happens, what do you get? You would still have the carbon with the double bond, but now it won't be to an oxygen, it'll be to a nitrogen. So that's this carbon here. How many carbons do we have before we get to the nitrogen? Well, how many carbons? This is going to form a ring, but how many carbons are going to be in this ring? We'll have this 1 carbon, 2, 3, 4, and then we'll have the nitrogen. That's a 5-carbon ring. So if you form a 5-carbon ring, we already have 2 of or a 5-atom ring. If you have a 5-atom ring, we already have 2 of the atoms in there. We just need 1, 2, 3 more. And you could see how this would be 1, 2, 3, 4, 5, just like we have over there. But the nitrogen has taken the place of the oxygen. And so that would be the whole product. The nitrogen already has its 3 bonds. We just replace the 2 bonds to the hydrogens with the 2 bonds to this carbon. So if you're thinking of a synthesis, notice it's a different thought process. You're not like thinking about every single step. You're thinking about what product you could possibly make. Okay, let's try another one for B. Another intramolecular imine formation. Now we're going to take these 2 hydrogens off, and the nitrogen is going to replace the oxygen. So we know we'll have these 2 carbons. We'll have the double bond there, but it'll be the nitrogen at the top of it, not the oxygen. So how many atoms are we going to have in this ring? We know it's going to form a ring because it's intramolecular, but how many atoms? We know this carbon is going to be there. We know each of these other carbons is going to be there, and the nitrogen is going to be in the ring. So it's going to be a 5-membered ring. So we'd have 2 in there already. We just have to add 3 more, and that's our 5-membered ring. So we'd have this carbonyl, carbon, the number 1, 2, 3, 4, and 5. Okay, well off of carbon 1 we have that methyl group which we already drew, and off of carbon 3 we have 2 methyl groups, so we just have to draw those in. Otherwise, that's our imine. That is our product. We have the sort of nitrogen version of the carbonyl, and the other R group was the carbon chain itself comes off and wraps around. Whenever you go from a straight chain to a ring or vice versa, it's always best to number everything. That makes it easier to follow along rather than trying to visualize. I mean, it's great if you can visualize how that happens, but if you can't, just number the carbon chain and make sure you have a chain that has the same number of carbons with things at the same numbered places. Okay. Well, what if we want to think in reverse? Here we're thinking about, in the last 2 exercises, we were thinking about if we have a ketone and a nitrogen, a ketone and an amine, what product can we form? What if we want to think in reverse? What if we have the product we know we want? How can we make that? Well, all you have to do is draw a line down the center where the nitrogen is. The carbon chain that has the double bond, that needs to be a ketone. And the other carbon chain is the 1 carbon chain coming off of your primary amine. So you'll always have those 2 hydrogens. And that's all you need. If you mix those 2 together, if you don't believe me, you can draw the mechanism. If you mix those 2 together, you'll get the product above. If you want to do the same thing with B, draw a line down the nitrogen. The part of the molecule that has that double bond, that will still have a double bond, but it'll be to oxygen. So cyclohexanone, it will be one of the reagents we need to form that. The other one will have the nitrogen, the carbon chain, and if you formed an imine, it's always a primary amine that you used. So you'll always have those 2 hydrogens. So those are your 2 reagents that you need there. Okay, this next one is interesting because here we have a ring. And at first glance, you might not have even thought that this could be imine formation, and yet it has the ketone in disguise. That ring on the left, that double bond to the nitrogen will get replaced to a double bond with an oxygen. How many other carbons do we have? Well, from this bottom one down here, 1, 2, 3, 4, and then a nitrogen. So if we're counting, this is 1. So we could have 2, 3, 4, and then bonded to the 4th one, the nitrogen. Now, in order to form an imine, you always have to have a primary amine, so you'll always have those 2 hydrogens there. And this molecule can form that ring. You could see how something like this would be useful in a biological molecule. First of all, it's very easy to get your hands on oxygen, all the water in the world. It's very easy to get your hands on amines. They can form from the air, because the air is mostly nitrogen. And there's a lot of hydrogen on Earth for it to react with. So you can have those, and you can see how a living thing could start to form rings in itself, and those rings are more rigid and fit more reliably into receptor sites and communicate biological messages. But also, the living thing can control how rigid the molecule is just by adding water and using Le Chatelier's principle. So this is just these last few problems are just to give you a sense of how you can think about the imine formation reactions, but from the perspective of synthesis, from the perspective of jumping, hopscotching from reactants to products.